Well, I make it 8 o'clock. Good morning, guys. How you doing? Can you hear me?
Yes.
Excellent. Thank you. I appreciate that. Does anybody have any questions, comments, problems, concerns, anything before we get started? Okay. And I will just get into what we're talking about today. So, what are we going to be talking about today? We're going to be talking about the periodic table, which is why I have one up. It's going to be a reference that we need today. We'll talk about quantum numbers, orbitals, electron configurations, periodic trends, molecules and molecular compounds, empirical formulas, ionic compounds, and naming. So we've got a lot of stuff that we're going to be covering today, but it's all building on what we've talked about previously. But let's do a little review if it will go there. So I asked you to draw me an atom of 13,9F minus, showing me the number of electrons, neutrons, and protons. So, okay, F minus. I know that F is number 9, so he's going to have 9 protons. His mass number being 13 minus 9, that gives me 4 neutrons. 1, 2, 3, 4. So these are my neutrons. Those are my protons, and these are my electrons. And of course, since he's an F minus, he has an extra electron. So I need to have 10 of them that exist around this thing for reasons that we will talk about today. I'm going to draw them looking like this. Not well drawn, but that doesn't matter. This is not an art class, so nobody's going to be paying attention to that. If I can count, that's 10. Go. Awesome. So all I really was looking for was one, that you could recognize how many neutrons were in it, two, how many protons were in it, and three, how many electrons needed to be there for that to be the charge that you're looking for. So any questions about that?
Yeah, how are we supposed to draw that on a quiz?
If it's on a quiz, what you're going to have is you'll draw it on a piece of paper and upload that. So I am looking for and that's a good point. I am looking for you to turn in your scratch work. I'm a big proponent of turning in your scratch work because if I don't have your work, then I can't give you partial credit for whatever you've done. And chances are you may have done everything right except some math error, in which case you should get the majority of the points. So there is going to be a Dropbox on D12 for all of your scratch work for each test. So I will expect that.
Okay, thanks.
Sure, no problem. Anything else? Okay. So here is our periodic table. Yay, it's a periodic table. And it's, fairly familiar to us. If you can tell from this yellow that's here, these two rows that are down at the bottom actually fit right here, and that should make the table much wider. But that doesn't fit nicely on a piece of paper, so we usually pull them out so that we don't do that. We're going to talk a lot about what exactly is on here and what all of this means today. Everything that I can possibly take back to link to the periodic table, I will. My reasoning for that is you always have a periodic table available to you on a test. So if you can link that information back to a periodic table, hopefully it will help you to build that information when you need it. Okay? So here's our table. Yay. Couple of things that we want to talk about on the table. We'll talk about groups, and our groups are the columns. Okay. We'll also talk about periods, and those are the rows that we have on our table. We'll talk about the types of elements. So the metals, which is most of the stuff on this table, the metalloids, which are the things that exist along this stair step, although this one doesn't show the stair step. There is a stair step that exists here, and actually, let me go back. Come on. There we go. So this set of guys here in light blue, that's the stair step that I'm talking about. So that's usually shown on the periodic table. It's not on this particular one. So good choice. Excellent. So those are our metalloids. And then we have our nonmetals, which is this corner up here. All right. It's important that we know whether it's a metal or a non-metal. We'll talk about why that's important today. But those are the things that we're going to be talking about in terms of those parts of the periodic table. Okay. Now, things that are in the same group have the same number of what we call valence electrons. We'll talk about what exactly a valence electron is, but it means that there's the same number of electrons in the outermost shell that we can deal with, and that determines a lot of the chemistry that we see, which is why these things are grouped the way that they're grouped, because they always have the same kinds of properties, and that's because of how many electrons exist in that outermost shell. Okay? Now, there are some groups that you will need to know the names for. So group 1A, this is this group right here. These are alkali metals, and that does not include hydrogen, even though hydrogen is in that group. Hydrogen is not a metal, so he doesn't qualify in there. But lithium, sodium, potassium, rubidium, cesium, and francium are our alkali metals. 2A is our alkaline earth metals, so beryllium, magnesium, calcium, strontium, barium, and radium. Okay, those are our alkaline earth metals. We also talk about our chalcogens, which are these guys right here. Oxygen down. It's the oxygen column. Our halogens, which is the fluorines, chlorines, these guys right here, and our noble gases. So the exterior portions of the periodic table are the ones that you need to know by name. Okay. The reason that you'll need to know that is you'll often see things referred to in your textbook as the halogens do this, the chalcogens do this, the noble gases do this. So those terms are very common, so we need to make sure that we know what those are talking about. You will also see this probably on a test in the sense that I will say you have a chalcogen and an alkaline earth metal. What kind of formula is that going to look like? Tell me some properties about that kind of thing. So that is something that you will need to be able to do. Okay, so those are the only groups that you need to know the names for. And again, that's the alkali metals, the alkaline earth metals, chalcogens, halogens, and the noble gases. Now, information that we should be able to get on a periodic table. Let's take a look and see if we can actually do one of these. So when I look at a particular element on this table, because this is an interactive periodic table, I can see that this is nitrogen. He is number 7. So that's his atomic number. Okay, that's also the number of protons that he has. His atomic mass for nitrogen is 14.007. And again, that's AMUs for a single atom, or 14.007 grams per mole. So if I have a mole, then that's how much it weighs. I'll be able to tell what group it's in based on its location in the periodic table. There we go. We'll be able to see if it's a metal, a non-metal, or a metalloid, depending on where it is in the periodic table. So if I'm looking at nitrogen, again, he's over here. He's to the right of that stair step that we talked about. So he is a non-metal. Okay. So those things are things that we should be able to pull from our periodic table. The tables that you have on the test will tell you all of those things. Okay. So those are pieces of information that are on any table that we look at. There are other things that are sometimes shown. You'll see that this one has an electron configuration. It'll tell you the key isotopes, density, first ionization energies, things like that. Those are not always present on these tables, but they are things that we can typically look up if we need them. Okay? So, questions about that? Now, the next thing we need to talk about are these things called quantum numbers. There are 4 types of quantum numbers that we deal with. There's N, L, ML, and MS. And N is a principal quantum number. It's the energy of the orbital. So if we're talking about orbitals, there is a 1 orbital, for the row 1. There's 2 orbitals in row 2. There are 3 orbitals in row 3. So the row number is what determines that energy level that we're talking about. So we have a bunch of rows, we have a bunch of row numbers, okay? So n is always the row number that we're in. L is our angular momentum. It has some possible values up to n minus 1. It tells me the shape of the orbital. You may have heard of this in terms of those shapes. So there are s orbitals, p orbitals, d orbitals, and f orbitals. Although there are g and h, we will not talk about those. Those 4 we will talk about in more detail in a few minutes, but that determines the shape of the orbital. Okay, so that's what that L is for. Now our ML is our magnetic quantum number. It's the direction in space. Now an S doesn't really have a direction because it's a spherical, so it's a sphere, yay. But a p orbital looks like a dumbbell, and there are 3 of them that we talk about. One of them is on the x-axis, one of them is on the y-axis, and one of them is on the z-axis. So ML tells us which direction that is. Okay, so that's what that's for. Now MS is called a spin quantum number. MS tells us whether it's an up or a down. Those are the only ways that we refer to the spin. The up is a plus 1/2, the down is a minus 1/2, and it's a 1/2 because that's why it's a spin. So that's why the number is a half as opposed to just an up or a down. So those are the values that we have for those. Now, is it important that you know all of the combinations of these things that can exist? For you guys, no. Is that something that sometimes gets talked about? Yes, of course it is. The only parts that we're going to be concerned about is how many electrons can exist in each of these types of orbitals. And we'll talk about that in just a few minutes. So questions about what these are or where we see them. Okay. Now, all this is referring to this thing right here. It's talking about the fact that we can have different values. So if my first row, right, if n is equal to 1, we're talking about this first row, then I know that the only value for the spin that I or for the shape that I can have is 0. That 0 means it's an s orbital, so it's spherical. And there's only one of them, okay? So I only have 2 elements that appear in that first row. That s orbital can only contain 2 electrons, okay? So it's a 1s. Every row has an s. Not every row has everything else. We add things as we go down. So in our second row, not only do we have an s, but we also have p, okay? So we have a px, a py, and a pz, as I just stated. So we have 3 of those p orbitals. Every orbital can contain 2 electrons. So that means in that second row, because I have an s and 3 p's, I have a total of 8 electrons that can be added in that particular row. So you'll notice 1, 2, 3, 4, 5, 6, 7, 8. 8 electrons that can go into the s, which is over here, and the p's, which are over here. You'll see that referred to occasionally, and actually I think it's on my next slide. Hold on, let me see if it's here. Yeah, this is shaped. Okay. So you'll see that referred to, and I know that I have a slide that shows this. We talk about these as being the S block over here. These 2 rows or 2 columns are the S block. This over here, these guys, those are the P block. This section in the middle is the D block. And this section down here is an F block. And that's because as we continue to add electrons to each of those things, that's where we're adding those electrons when we're in those spaces. So we're adding to the S block here, we're adding to the P block here, we're adding to a D block here, and we're adding to an F block here. Okay. And we'll talk about how we add them in just a minute. Like I said, there are 4 different types of orbitals that we'll be talking about. We have S, P, D, and we don't draw the Fs because they're really complicated. Our S's are always spherical. They get bigger as we go down the table, which makes sense. We have a higher energy as we move away from the nucleus, so they're bigger. We have our p orbitals, again, x, y, and z. There are 2 electrons in each of them, so total of 6 that can be added within those s orbitals. Okay. When we talk about our d orbitals, there are 5 of them that exist. This is what they look like. I won't ask you anything other than what are they shaped like, and the answer that I would be looking for there is cloverleaf. We don't talk about this one because that's a mathematical combination of a bunch of them, but they're cloverleafs. Okay, each one can contain 2 electrons. So again, if I have 10 of them, that means that the total electrons that I can have in those Ds is 10. So 5 electrons, 2 each, that's 10 electrons that I can put in there. F, there are 7 of them. Since there are 7 of them, that gives a total of 14. You'll notice that we only have odd numbers when we do this. So 1, 3, 5, and 7. So when we're talking about how many electrons can go in each of those, it's always based on 2 electrons in the number of orbitals of that type. So 2 here, 4 here, or 2 here, 6 here, 10 here, and 14 here again. Okay, so questions about that? Now, the next part we have to talk about is the energies of those orbitals. And while I would love to tell you that this is an easy thing for us to talk about, it's not necessarily. 1s is lower than 2s. That makes sense because we're closer to the nucleus, so that makes sense to me that it takes less energy to put it into that 1s. The 2s being further out is a little bit higher. The 2p, because it's more complex, is a slightly higher energy. I know that the next one is 3s, and then I would expect to have a 3p, and then in my head, I would expect the next one to be a 3d. We do have a 3d set, but it's not the next one that fills. And there's reasons for that. Okay. One of the reasons that we don't fill the 3d next is because the 4s and the 3d are almost the same energy, but the s is a lot smaller. Getting it half full or completely full is a lot easier than getting the d half full or completely full. And that's because there were 5 of them. Okay, so we fill that 4s first because we get special stability when we've half filled an orbital or completely filled an orbital. So that s is much easier to get that stability from than it is for the d. So that means that we start getting funky places where these things fill, right? And you may have seen this diagram in the past. This is something that some people use to tell you which way these things fill. And there is that. I don't particularly care for that, but I do know that there is another way to go through this. Did I hear a question? Okay, sorry. So I know that there's another way for me to figure that out. Now, I know that this first row contains an s, and that s can contain 2 electrons. So S1 and S2 in that first row. I then go to my second row, and I know that my second row has an S and some P, right? So for the S, I have 1, 2 in that S. Then I come over here and I have my P's, and I have 1, 2, 3, 4, 5, 6 that go in the P. I then go down to 3. This is my third row. And I have that S, and that's 1, 2 in the S. And then 1, 2, 3, 4, 5, 6 in the P. Notice the D hasn't filled. There's nothing in this D block in this third row. And so that's how I know that that's not the order of filling, because there's nothing there. Nature hasn't filled it that way, so it doesn't go in that order. So I go through my 3S and my 3P, and then I come to my 4S. Then I go to 3D, and it's always n-1. Our D block is always n-1. Okay, so the D is always 1 less than the row that it's in. Okay, so we have our 4S, our 3D, and again, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 of those. And then we go back to the 4P. Now, the only time that things get weird, again, is when we go down to the Fs, okay? And notice that we don't come into the Fs until right here, so this row right here. That F will fill before the D in that row, and our F is an n-2. So since this occurs in the 1, 2, 3, 4, 5, 6th row, this will be a 4F, okay? But that should show you the order of filling. I just follow the periodic table. So I know that it's an S block here, a p block here, a d block here, and an f block here. So if I can figure out what the numbers are and the order in which they fill, which the table shows me, then I should be able to determine an electron configuration. And we'll talk about that in just a second. Questions about the order of orbital filling?
I have a question.
Yes.
So, is the electron configuration to make up the protons or the group number? If that makes sense.
Well, it's to count the number of electrons. So it should be equal to the protons as long as it's not an ion.
Okay.
Yeah, so it should equal your atomic number as long as it's not an ion. Anything else? Okay. I knew it was here somewhere. So here's my S block, here's my D block, here's my P block, and here's my F block. You'll notice that this says n-1, this is n-2, and this shows my row numbers. So 1, 2, 3, 4, 5, 6, 7. Okay. So that is what I was talking about in terms of how we know what those numbers are. All right. So you may get asked, where's the S block? Where's the P block? Where's the D block? Where's the F block? You might get asked something like, how many electrons can an S orbital contain? How many electrons in total can P orbitals contain? How many electrons can D orbitals contain? That kind of stuff. So that is something that you may get asked. Questions about that? Now, when we talk about our electron configurations, we need to account for where all of the electrons live in this particular orbital, or particular element. And the reason that we need to know that is because, again, I need to know where those outermost electrons live, because that has a lot to do with the chemistry that it can do. And we'll talk a lot more about that in a bit. I know that electrons have spin, so they're either up or down. And we show that by drawing arrows in for each electron. So there are ways that we can draw these things. And I'll do that on the next slide to show where those electrons are. Okay, so we'll draw one up and one down because I have a +1/2 and a -1/2 for my spins. That's the Pauli exclusion principle. So that tells me that they have to have different spins. I can't have two electrons in the same orbital with the same spin. Can't happen. Hund's rule states that electrons do not pair, i.e., have the same location, have the same spin or have the same location unless they have to. Now, let's think about that for a second. If you have the option to have your own room, isn't that normally what you would take? You would have your own space if you had it, right? So as long as they have the ability to do that, i.e., they have the energy to get into another orbital that is not occupied, they will do so. Okay. If they don't have enough energy to get into the next unoccupied thing, i.e., it's a different type of orbital or it's a different level, then they can't do that. So that's when they'll start to pair. All right. So that only applies if there's more than one type of orbital. So since we have our S, we go one and then one up and then one down. That's typically how we draw them. It's always the up first. It's just convention. It's not important, just convention. But when we talk about those P's, remember that we have that PX, a PY, and a PZ. When we fill this, we'll go one there, and then the second one goes into that next one, rather than both of them being in that PX. Okay, so we really don't talk about, for the most part, which specific orbital they're in. However, we do need to know what Hund's rule tells us. So that's what Hund's rule is about, is that we're not going to be in the same place if we don't have to be. Okay. Now, when we talk about the electron configuration for a hydrogen atom, he's number 1 right here. So number 1, he's in the first row. That's 1. It's an S-type orbital. So that's a 1s. And there's 1 electron in it. So his electron configuration is a 1s1. Okay? And that's the only electron that we have to deal with in that electron configuration. All right, awesome. That's exciting. For anything that's beyond that, for our elements and our atoms, things that aren't charged, we're just going to need to follow the periodic table. And what I mean by that is that if I wanted to talk about helium, who's number 2, he's still in that first row. I only have an S type in that first row, and I have 2 electrons that need to go in that, and he's at 1s2. And remember, there's some weirdness in this first row because hydrogen is not an alkali metal. Helium is a noble gas, but he's still filling an S block. Okay, so they're a little bit different than everybody else on the table. Okay, and again, that's only because there are only 2 electrons in that particular group. So he's a 1s2, 2 electrons. Awesome. If I talk about lithium, I know he's in the second row, so I have to build on what I already had. So he's already got that 1s2 that came from the helium. And that next electron that I'm putting in is in the second row. It's an S-type orbital, and there's 1 electron that goes in there. Okay. When we talk about beryllium, we then add that again to that 2s, so that it has 2. Now my 2s is full. The next thing that I go to is a 2p over here in this p block. So boron, we're going to have that same core, the 1s2, the 2s2, and then a 2p1. Okay. And then we would do 2p2 for carbon, 2p3 for nitrogen, 2p4 for oxygen, 2p5 for fluorine, and 2p6 for neon. Okay, we'll come back to this and I'll show you all of them in a few minutes. All right. Now, that's how we do our atoms, things that aren't charged. Okay, so we follow the table, fill it according to what is on my table. Awesome, that's great. But what if I have to make an ion? So if I make an ion, I'm either going to be taking away an electron or adding one. Okay, when I do that, I always take electrons from the outermost shell. Okay, when we talk about the outermost shell, it's going to be whatever is on the edge. All right. So if we're talking about this being my electron configuration, a 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, I can tell 1, 2, 3, 4, the s is full, the 3d10 is full, 4p6 is krypton. If I then take an electron from that, I would take it from this 4p because that's the last thing that I filled. And so then that would be a 4p5 when I take 1 out, and he'd be a Kr plus because he's lost an electron. Okay? So we'd take it from that 4p. If we add, we always add to the outermost shell. If we were to add to this particular species, since my 4p is full, the next thing I would be adding to is that 5s. Okay. So if I were to do that, that would be a 5s1 that I would be adding to that. Okay. All right. Now, there are some weird exceptions that exist. They exist mostly in the D block, and we'll talk about those in a few minutes, but they do exist. So there are some, and they are predictable weird exceptions. Okay. So any questions about that? All right. Now I said that I'd draw you some pictures. So here are some pictures. We talked about the electron configuration for lithium, and I said that was a 1s2, 2s1, right? Because he's here. So he's in that second group. We had an S, we add 1 to that S. So my 1s is 1 up, 1 down, and then my 2s is 1 up, because that's all I have. When I go to beryllium, that next one, I said that was a 1s2, 2s2, so that's here. So I have that 1s, 1 up, 1 down, 2s, 1 up, 1 down. When we go to boron, which is again on this other side, over here, we're looking at a 1s2, 2s2, 2p1, because he's in the p's. So my 1s, 1 up, 1 down, 2s, 1 up, 1 down, and 2p up. And like I said, it's just convention that we always draw them up. It's not important that you get that it's up. It's just important that you have a convention for doing it. I.e., always do one of them before you do the other. Sorry. So there is that. So this is how I would draw all of these wonderful things that we've dealt with so far. So we get out to our neon, that's a 1s2, 2s2, 2p6. We got to that. We have our 1s, one up and down, our 2s up and down, and then our 2p up. And of course, when we fill the p's, we go 3 up, and then we do the 4 down, right? And then the 5 down, and then the 6 down. So there we have our pairing. Again, that's Hund's rule. All right, so questions about that? So on a paper test, you would get asked to draw these things. You might get asked to do one of these on the test. I might ask you to draw me one. But typically what you'll see is that I will ask for the electron configuration to be put into the test, and then I will ask you to draw it as well. And then that part you would upload. That allows me to grade it a little bit faster. So how would you enter this on a test? It's a good question. Because we don't typically have the ability to do the superscripts for these things. Sometimes we can, sometimes we can't. And so the way that this would get entered on a test, if we're talking about this lithium right here, we'd be talking about 1s2, 2s1. Space in between them. And again, I'm so used to writing it as a superscript. So I would just put this in as 1s2 space 2s1. And again, there's no superscript available there, so that's typically how you would enter that. All right. Now, if you don't enter it that way, if you end up doing something like a 1s and then caret 2, that will get full credit. It just won't look the same to the computer, and so it won't grade it that way. I'll have to go back and grade that, so your score will look a little bit lower if you do it that way. So it's not a big deal. You'll get the points back, but that's the recommendation for entering on a test. Questions about that? Okay, awesome. So I want you to do some practice. I want you to try and write electron configurations for elements 1 through 12. Okay? And I will walk through exactly what these look like in a couple of minutes. So if there are questions while you're working through that, go ahead and yell them out. We can talk about that. But I want you to do the practice. Now, is it important that I know how to do this? Sure, absolutely. That's what they pay me for. But it's also important that you know how to do this. So I need to give you time to practice where you can ask questions if you have. So go ahead and do some practice on these. Again, I'm looking for 1 through 12. I'll show you the table so you can see that. So we're going from hydrogen up to magnesium. Okay. Anybody want more time before I start talking through this? Okay. So when I'm looking at hydrogen, again, he's over here in an S block. So hydrogen, he's in row 1, he's in an S, he has 1 electron to put in. Helium, even though he's on the other side, is still in that S block. He's in row 1, he has an S block, he has 2 electrons to put in there. Lithium is in the second row, so he's got that 1s2 full. He's then got the 2s, and there's 1 electron that goes in the 2s. When we talk about beryllium, we've got the 1s2, 2s, but instead of 1, we now have 2 in that 2s. When we talk about boron, he's now in a p block, so he's over here. So again, I have the same core that I had before, the 1s2, the 2s2, and then a 2p1. When we talk about carbon, he's got that 1s2, 2s2, 2p2. Nitrogen is a 1s2, 2s2, 2p3. Oxygen is a 1s2, 2s2, 2p4. 1s2 for fluorine, 2s2, 2p5. And my neon is a 1s2, 2s2, 2p6. My P can't contain anymore, so I'm done there. Yay, awesome. So now I'm going to go back to a new S block. Okay. And I go down to row 3, that is an S block. So that means that I still have that 1s2, 2s2, 2p6, but now I have a 3s1. And then magnesium, that 1s2, 2s2, 2p6, and then 3s2. Okay? So we just, whatever we had before, we're going to keep adding to that. And of course, if I need to do this, and I mean, I've been doing this for ages, so it sounds like I know exactly what I'm talking about. And that's just because I'm used to doing this. 1s2, 2s2, 2p6, 3s2, 3p6. And I know that because they're always full if I'm past that. So I know that that's what core I'm talking about. So it's fairly easy for me to get to, okay, everything except that last row I know. And so sometimes what you'll see is that instead of doing all of that, like if we were to talk about sodium here, what you might see instead of seeing this, the full electron configuration, we know that it's the same core as the noble gas before it. So this neon, right? It's the same core as that neon, and then we're adding a 3s1 past that. So that's a shorthand notation that we sometimes use for this because we know it's exactly the same as that noble gas before it. So we can use that noble gas notation to indicate that it's got that core, but then we have these things after that. Okay, so my Mg would then be that neon core, and then a 3s2. Okay, so that's our shorthand notation for the noble gases. Sorry, I was writing stuff and you couldn't see that. I'm so sorry. So questions about that? All right. So our condensed electron configuration, the noble gas notation, uses the noble gas closes the element with going over the element's atomic number. So like I said, that neon before. We put the noble gas in brackets and start the electron configuration with a noble gas left off. Okay? You may get asked for a full electron configuration, which indicates all of the electrons that are present in their particular orbitals. You may get asked for a noble gas notation, which would be that shortcut that we just talked about. You may be asked to do both of them in a particular question. Now, when we talk about things that are a little bit different, a little bit further down, we start talking about these transition metals. We're talking about 3D filling here because that's our first D that we have. Everything looks perfectly normal when we get to Ca, right? So we get to Ca, and he's in this 4th row. So 4s1, 4s2 for Ca. That makes sense. Then we go scandium, and that's that 4s2, 3d1. Now, some sources will show you that the D is first rather than the S. I don't care which way you put it because it's a debate as to which should go first. There are some people that are very emphatically against putting it second because all the threes should go together and all the fours should go together. Frankly, I don't understand that. If it fills in a different order, shouldn't we write it in a different order? So that's how you see that I do it. So again, for scandium, I'd write this as AR 4S2 3D1.
I have a quick question.
Yes.
Do you mind going up to the slide again? The one that we were supposed to practice?
Yes. Let's go back. Yes.
Okay. Thanks.
Sure. No problem. So again, you'll see sometimes that the 4S is written first, the 3D is written first. Both are okay. I don't care which way you do it because it's they're both fine. There's no reason to do that any different. And everything looks great until we get to this point where we have 1, 2, 3, 4, 5. Well, okay. This looks normal. This looks normal. But then I go here and that doesn't look normal to me. Why doesn't that look normal to me? Because instead of having the 2 electrons out here, like we had in all of the previous ones, we've taken one of them and moved it in there. That's weird. Why did we do that? And the reason that that happens is because, again, when I have an orbital that's half full, I get some particular stability from it. So having the half full D and the half full S is more stable than having 4 in the D and 2 in the S. Okay, they're very similar in energy, that 4S and that 3D. So we get additional stability from having them both half full. So that's why that exists. You'll see that that happens for the chromium, this one that has the notation here, and for copper. That's the other place that this happens. And what you'll find is that that's this group right here and this group right here. Those groups always behave in those ways. So that's something that we know happens. It's unusual, but it's predictable. Okay. You may get, and actually, let me not say it that way. You will get asked about that. Okay. So you will get asked, what is the electron configuration for this? Why is it unusual? That kind of thing. And one of the things that we would talk about is if we were to make an ion out of this particular species, where would we take the electron from? So if we talk about chromium, this 3D5-4S1 that's written here, if we were to make that an ion and make it a Cr+, we would take the electron from the 4S because it is the furthest away from the nucleus. So that's the one that we would take off. So a Cr+ would be that AR and then 3D5. So we've removed that 4S. So the one that has the largest principal quantum number is where we'll take that electron from. Remember, when we talk about taking them off or putting them on, it's always the one that's furthest away from the nucleus. Okay? So questions about that? I'm only showing you the electron configurations for the lanthanides and the actinides to show you that the exact same thing happens in those groups. Okay, it's not important that you know how they happen or that you can write these. I'm not going to make you, frankly, I don't want to have to grade an electron configuration that's that big, so I wouldn't ask about that. But these same things happen here, and they happen for the exact same reasons. Okay? All right. So, questions about our electron configurations? Because we're going to change gears a little bit here. And we're going to start talking about periodic trends. The first periodic trend that we're going to talk about is effective nuclear charge. And so if I move my table, and it's not going to show up very well, as I go across a row in the table from left to right, so as I go from sodium over here to argon, I'm adding both protons and electrons, right? So I've added more protons in that nucleus and more electrons in this outside, sphere that exists there. But the nucleus is much more visible to all of those electrons than the other electrons. There's a big amount of space between all of those electrons, and they don't necessarily see each other that well if they're in the same group, because they're the same distance from the nucleus. So they don't always see each other. But I do see that additional proton that got added. And so the fact that I have more protons and we have electrons that don't necessarily see each other means that what happens is, as we go across this way, that additional positive charge that we have in the center pulls all of those electrons in more. So as I go from sodium over here to argon, the size gets smaller. And that's because the effective nuclear charge gets bigger. So my nuclear charge gets bigger, my size gets smaller. Now, the other thing that we need to talk about in terms of size is, as we go down, we're further away from the nucleus, that is bigger than the rows above it. Okay. Is there anything else I need to say? Yeah. So, and of course, the effect vertically is much smaller than what we see horizontally. Right. So even though stuff in row 3 is going to be bigger than row 2, it's not as big of a change as we would see as we go across the table. Right. So effective nuclear charge is higher as I go from left to right. It's also higher as I go from top to bottom. So effective nuclear charge is that. Questions about that? Atomic radius, again, same trend that we were talking about, and it's the same reason why. Okay, so, and I always list this as smaller that way, and then this way. And in my head, that makes more sense, but it's up to you how you decide to do it. What you'll be asked for these things is which direction does it change, i.e. which is bigger, which is smaller. And you may be asked to compare 2 different elements. So I might ask you which is bigger, K or Ca, that kind of thing. Okay. I will mention the ionic radius. So as we add electrons to these things, we get bigger. As we take them away, we get smaller. The reasons are much the same as what we talked about, but as you can see from this figure right here, it's not very predictable. And so I am not concerned about you knowing which one is bigger or which one is smaller based on the ions. It is important that if you go forward, i.e. into organic chemistry, that you understand this. But for us, it's only important that we understand what happens based on the addition of electrons and the addition of the protons. So the atomic radius is far more important than the ionic. Questions about that? So I won't specifically ask you about ionic radius on the test. It's information. Okay, next thing we're going to talk about, ionization energy. Now, ionization energy is defined as how much energy is required to be given to an atom to remove an electron. So how much energy I have to add to take that electron off. Ionization energies increase as I continue to remove electrons. So if I have something where I've taken off one of them, and then I want to take a second one off, that's going to be bigger than it took to get the first one. Okay? And that makes sense, because as it's already charged, it's harder to take that second one off. All right. There's a very large increase in ionization energy when you remove an inner shell electron. So if we're talking about something where we have a full shell, so if we were to look at sodium right here, sodium is very, very happy to give up one electron because it has that 3s1. So it's happy to give up that 3s1. But if I were to try and take one of the 2s from an inner shell, that's a much bigger deal. Okay. So we want that shell to stay full. It is full. We want it to stay full. 3s, because it's not, it's fairly easy for us to pull that one. Okay. It generally increases as I move from left to right. And that makes sense to me as well. And the reason that it makes sense to me is because everybody wants to be a noble gas. Why does everybody want to be a noble gas? Well, there's lots of reasons for that. Part of that is because that shell is full, and so there's stability that comes from that. So if my shell is full when I get to the noble gases, and they're called noble because they don't do a lot of chemistry, then that's a particularly good place for me to be. So if I'm over here as a non-metal, I want to add electrons to become like the nearest noble gas. But if I'm a metal, it's easier for me to lose electrons to be like the nearest noble gas than it is to gain enough electrons to be like the next noble gas. Okay, so that's why we typically see metals having positive charges and non-metals having negative charges. Now, there are some weird exceptions. They tend to be here in the middle. We do have some weirdness that goes on with some of the non-metals. It happens. But that tends to be what we see. Okay? So that's why that is that way. So for me, there's a lot to be understood from, okay, where is it going to be easier for me to lose or gain electrons? And that's because I want to be like that nearest noble gas. Okay? So as I move from left to right, if I'm over here and I actually want to gain electrons, it's going to take a lot of energy to pull one off. Okay? So my ionization energy is going to increase as I go from left to right and from the bottom to the top. And again, that's because I'm closer to the nucleus as I go up. So it's going to be harder for me to deal with that. Okay? Now, electron affinity. What is electron affinity? Well, the energy change that happens when an electron is added to an atom. Okay? So for nonmetals, that's energy that we give up. Okay, so that's good for us. It's favorable for us to get those electrons added to us, and so that energy is given up. For metals, it's the energy required to add it. Okay, note that the energy being released is negative. Positive energies are required to add. So the most favorable is adding to F. Where's F? He's up here. He's right here. So my most favorable location is to add to this guy right here. He wants them the most. So it's most favorable for me to do that. Therefore, he's the most negative value. Okay? And so we're going to increase going down and left. Okay? Yay! Isn't this fun? Yeah. So here are my trends. Ionization energy, electronegativity, which we actually haven't talked about. I'll talk about that in just a second. Electron affinity, atomic radius, metallic character. So I know that my metals are over here. We are more metallic as we come over here, and we're more non-metallic as we come up here, because that's where my non-metals are. And when we talk about electronegativity, okay, since we haven't actually talked about that yet, electronegativity is related to that electron affinity. So electronegativity is a measure of how much a particular element wants that electron. So it's the same idea, it's just looking at it in a different way. So how much do I want it? How much am I going to be able to pull it? Technically, electron affinity is a measure of how much it wants it when it's a single electron or a single element or an atom. When we talk about electronegativity, it tends to be when it's in a bond. And so based on its location, which one wants those electrons more? Okay. So when we talk about electron affinity, the same trend is going to hold for electron affinity as it does for electronegativity. Okay. Questions about any of that? All right, let's change gears yet again. Isn't that fun? Yes. So let's talk about molecules and molecular compounds. So molecular substances are things that contain nonmetals bonded to other nonmetals. This is why we have to talk about them again, because we're talking about bonds that are made with all of these guys, right? So nonmetal to nonmetal bonds, those are molecular compounds. So they can be the same element as in O2 or different elements as in CO, okay? We use the atomic symbols and subscripts to convey the proportions of that compound. H2 is diatomic because it contains 2 electrons. H2O is polyatomic, meaning it contains more than 2, although polyatomic does actually apply to 2 as well. Molecular formulas are those that represent exactly how many of each atom are in the formula. So if we talk about H2O2, I have 2 hydrogens, 2 oxygens, but it has an empirical formula, which is just HO. An empirical formula is the smallest whole number ratio for the atoms in that formula. So HO, because I can divide both of them by 2. Okay, so that our moleculars are always going to have the exact number that we have. Our empirical is the smallest whole number ratio for them. Okay. When we talk about those, we're always talking about molecules, so nonmetal to nonmetal bonds. All right. We can talk about molecular models, and the reason that I'll talk about this is just because if you're looking at things on the internet, you may see them in different ways. Depends on who did it, what you're going to see. We can see molecular formulas, which have the exact number of these things that are here, so an H2 and H2O, that kind of stuff. Could be a structural formula, which shows you explicitly who is bound to what and in what order. We can see ball and stick models. And the reason for the ball and stick models is because then I get a relative size of what these things look like when they're bound to each other, and it explicitly shows the bonds. We can also have a space filling model, which shows us really the density of the electrons that exist in this thing. We won't talk about that really at all because that goes into how they share and what they share and stuff like that. And that's not really something that we talk about. But these are different ways that you will see the same thing represented. So I can see H2O, I can see HOH, I can see the O in the middle here bound to an H and an H, and this oxygen, which has all of the electron density, and the 2 hydrogens that are sticking off of the side of it. Okay? So questions about any of that? I mentioned an empirical formula. All right, it's the smallest whole number ratio of the molecules or of the elements that exist in that molecule. Those are typically determined from experiment. Smallest whole number ratio of atoms in the molecule. So H2O2, again, hydrogen peroxide, is a molecular formula. Describes everything that's in it. We wouldn't get that from experiment. We'd get HO. That's an empirical formula. Okay. We need to know how to determine the empirical formula from a molecular formula. And we'll talk about how we do that in the opposite direction in a little bit. So how would we do that? Well, that should be not that complicated. Come on. Oh, there we go. So if I want to determine an empirical formula for the following molecules, I want to know what's the smallest whole number ratio for them. If I have a C6H6, I can divide everything by 6, right? And I end up with a CH as my empirical formula for that. All right. If I look at an N2O5, there is no common number that I can divide both of those by to get anything else. So my empirical formula for that is N2O5. If I look at C4Cl4, both of those are divisible by 4, so my empirical formula is CCl. If I look at PCl5, I have no common denominator, so PCl5 is my empirical formula there. And if I look at C6H12O6, I can divide by 6 to get a CH2O. Okay, so that's one of these things. We may ask you what's the empirical formula for this particular molecular formula. Now, what's the relationship of the molecular formula to the empirical formula for each of these? By what number do we have to multiply these to get the molecular formula? This is one of the other things that we can ask you about. So we talked about C6H12O6 having an empirical formula of CH2O. If I tell you that that empirical formula is CH2O and I tell you that its ratio is 6, then you should be able to get from this and this back to that. Okay, so if I have an empirical formula of CHO and my ratio is 3, that means that this is C3H3O3. Okay, just the multiplication. That's all we're doing for that. If I have a B5H7 and its ratio is 2, that's a B10H14. We can simplify my C4H2O2 to C2HO. We can take a CH2, multiply that by 2, it can be 2C2H4. And then a C4O2 can become C2O. And of course, this 2 and this 2. Okay? So you may get asked something like that. What is the ratio of these things? What is the molecular formula if this is the empirical formula? Typically, that would be involved in determining what the molecular formula is if you know that once we've determined an empirical formula and you're told what a molecular weight is. Okay, we'll talk about that in a little bit. So questions about how we determine our ratios or how we use those. Okay. All right. Now, we talked about molecules, which are things that are made from non-metal. But we also need to be able to talk about ions and ionic compounds. Now, what was an ion again? It's something that's either lost or gained an electron. So if I talk about Na, and actually let me pull that back here. So if I talk about Na, who's right here, it wants to become a noble gas. So lose that electron to be like the noble gas before it. And of course, the noble gas before it is this neon. So it would lose that 3s1 to become like neon. When it loses that 3s1, it then has a positive charge. Okay, so Na plus is an ion. It's a charged particle. Ionic compounds are formed between metals and nonmetals when those atoms have become ions. So if the metals want to lose electrons to become positively charged, and my nonmetals want to gain electrons to become negatively charged, those things are going to be electrostatically attracted to each other, and they can make ionic compounds. Okay? Now, they mix in fixed ratios based on their charges, and that makes sense because if I have an electrostatic charge, then I'm going to want to make that a neutral. Okay, so I need to have the same number of positives as negatives. Now, we do have some notation that we need to talk about here. Positive ions are called cations. Negative ions are called anions. Okay? So that is something that you'll need to be aware of because you may get asked, what's the charge on the cation? What's the charge on the anion? So you'll need to know which one is which. Okay. We can predict ionic charges. That's awesome. And the way that I do that is by looking at where is this thing. So we talked about sodium wanting to lose one electron to become like neon. So I would expect that he would be a +1, right? And that's going to be the case for all of these guys. They want to lose one electron to be a single positive charge because that takes them back to be like the nearest noble gas. My alkaline earth metals are going to have 2 electrons that they want to get to be like the nearest noble gas. So I'm going to have my alkaline metals +1 alkaline earth +2. Turns out that things get complicated when we start talking about the guys in the middle, right? These things can do a lot of different things, so we aren't necessarily going to be able to predict those as easily. One of the things that I can tell you is it's fairly common for them to have a +1 or a +2 charge, but you would have to be explicitly told what that charge is. I'll show you how we do that in a little bit. When we talk about our nonmetals, we can predict what their charges are based on how many electrons we would expect them to gain. Okay. So if we talk about carbon, we would expect that he would gain 1, 2, 3, 4. So we might see him being a C -4. Nitrogen being as an N -3, oxygen being a -2, and F being a -1. Okay, we predict those for the chalcogens And again, those are the ones in the oxygen column as being a -2, and our halogens as being a -1. So those are the ones that are very easy for us to predict. Okay? You will find that the metals that are right here, like aluminum, he tends to lose the 3 electrons that he's got to be like neon. So there is that too. But that's typically something that we can predict and work through. So we said that lithium, being an alkaline metal, is going to lose 1 electron to be an Li+, right? We said that oxygen, being a chalcogen, and being over here, he's going to go on to gain 2 electrons to be like neon, so he's going to be -2. We indicate their charge as a superscript on the right-hand side. That calcium, again, being over here, right here, he's going to be a +2. And my chlorine, being a halogen, is going to be a -1. Okay? So those are things that we can predict. Awesome. Well, now I know what their charges are. That's fun. And we can do a whole bunch of practice with these. I would like you to do that to see what you can get from these. I'll give you a minute to do that. And the reason that I'm going to enforce that you do this, that I'm going to make you do this at this point, is because it's really important that we know what those charges are going to be able to do everything that we're going to be doing from here on out. So practice is extremely important. So let us practice and determine what our charges are for each of these. And I'll do this. Hopefully you can see everything now. Right? I can't find my chat button. Yes, that's okay. This will be recorded. You can look at it later. And I did put up the recording for the second lecture. I apparently can't get my hands on the first one because even though it saves to the cloud, the university will not allow me to find it. Yay. So I've had to change how I record them. So I apologize for that. Sure, no problem. Okay. Anybody looking for a little more time before I run through? All right. So when I do this, I say, okay, I'm looking for S. S is over here. He is a chalcogen. Since he's a chalcogen and he's 2 over from the noble gas, he's going to gain 2 electrons to become like the nearest noble gas. So that means he's going to be a -2 charge. When I talk about strontium, he's right here. He's an alkaline earth metal. He has 2 electrons in the S that he needs to lose to be like krypton, which is the noble gas before him. So he's going to be a +2. Potassium being here, he's an alkaline metal. He'll lose 1 electron to become like argon. So he's a +1. Fluorine is a halogen. He needs to gain 1 electron to become like neon. So he's going to be a -1. Calcium is here. He's an alkaline earth metal. So again, he's got the 2 S electrons he needs to lose to become like the nearest noble gas. So he'll be a +2. I'm going to skip nitrogen for just a second. I swear I will come right back. Iodine here is a halogen, also going to gain 1 electron. Ba, alkaline earth, will lose 2 electrons to be a +2. Cs, right next to him, is an alkaline metal. He's going to lose the 1 electron, so he's a +1. And Se, where's my Se? No, he's right there. He is a chalcogen, and he's 2 over, so he's going to need to gain 2 electrons to be like the nearest noble gas, which is krypton. I said I would come back to nitrogen, and the reason I'm coming back to nitrogen is because he's not in a named group, but he is a nonmetal. He's going to have to gain electrons to become like the nearest noble gas, which is neon. He does so by gaining 1, 2, 3 electrons. So he's going to be a -3. So even though he's not in one of our named groups, he's still something that I can predict. Okay. I mentioned that aluminum is also going to be a metal that loses three electrons. So, and he loses the 3 because he's got the 2s and the 1p. So he'll lose those 3 electrons to become like neon. Okay, so that's how we do our prediction of charges for those guys. Questions about that? Cool. Now, here, common monoatomic ions of the main group elements. You'll see that my 1A group, those are all +1s. My 2A, those are all +2s. You'll see that my 3, these all of the metals tend to be +3 charges, although Tl can also be a +1. That's where he's lost only that P. Okay. The boron, carbon, silicon, and germanium tend to not be charged per se. We'll talk about what they do in a bit. And that's because they're metalloids. So they don't tend to have an actual charge. Nitrogen is a -3. Bi is going to be a +3. Sn will be a +2. Pb is a +2. I'm not going to ask that you know these guys or this one. So these metals over here, that we're not going to worry about. Aluminum, yeah, that one okay, but not these. Okay. Nitrogen, all of these non-metals, yes, those I want you to know. Now an H can be either an H plus or an H minus. It depends on where it is and what it's bound to, what it's going to do. Okay. So those are our charges. And again, I hope that we can see from the periodic table why they do what they do. Okay. Now, on your test, do you have to remember all of these things? Well, it depends. We typically do have polyatomic ions. I do not expect that you remember the name of those or that you remember the charges for them. But if you see a name, you need to be able to figure out what that formula is. If you see a formula, you may need to know what the name is, because you may have to say, okay, what's the name of this compound? So you will see that there is on the exam handouts, there is a list of common polyatomic ions. So you'll have that available to you. It's on page 3. And it's just what you're looking at here. So you'll get the name and the formula with the charge. So I will expect that you can tell me what those charges are and that you can use those appropriately. So make sure that you're familiar with the list so that you know where these things are. Okay? Questions about our polyatomics. Some of these will work with a lot more than others, so you'll get used to some of them, but they'll always be available to you in that list. And the reason I say that is because half the time I have to look them up if I don't work with them all the time. So why wouldn't somebody else? Now, what are the charges on the D and F block metals? I said that it was going to get complicated and that things would be weird when we talk about these Ds and these Fs. So I know that these Ds have S's that they can lose. It's fairly common for them to do so. Sometimes, like this one, it only had that one S electron because it had moved the other one into the D block. So sometimes they only have the one and then they become a +1. So there are some things about those. You don't necessarily know what that charge is going to be, but if I tell you that Cr is a plus, or if I tell you that it's a chromium 1, this number that exists in that in parentheses after that name tells you the charge. Okay, and since it's a metal, I know that it's going to be a +1 because it is a metal, so we'll have lost those. Okay, so you'll either need to see the charge on the metal, the name of the compound, or from inspection. Now you may be able to determine that from inspection. Talk about that in a little bit. So questions about those guys. And if on a test you don't know what it is, if it's ambiguous and it says, oh, we're dealing with titanium, and I didn't tell you if it was titanium 2 or titanium 1 or whatever, just tell me I decided this was, and I can work with that. Okay, because if I have forgotten, that is my problem, not yours. Okay, so seeing the charge on the metal, we would see Fe2 plus, Fe3 plus, Cu2 plus, Zn plus. That's an actual explicit charge. That's what it's charging. The name of the metal, iron 3 oxide, zinc 1 chloride, copper 2 oxide. Again, it's that first one would be Fe3 plus, Zn 1 plus, and Cu2 plus for those names. From inspection, I can see that when we're talking about that iron 3 oxide, that's this one right here. So I know that oxygen is a -2 based on where he is in the periodic table. So if he's a -2, then I know that I need to have 2 of those Fe's to make that work, okay? Whatever that charge is. And so if it's either, so I know that I need to have 2 of them to make that work. And they have to have a common charge, i.e. they have to have the same net charge. So if my oxygen is -2 and there are 3 of them, then that means I have a total of -6 for my negative charge. Fe, since there are 2 of them, has to be positive. There have to be two of them. That means that one has to be a +3. So opposite charge, we take that 2 that's there and divide that into the total charge to tell us what the charge is on each of those ions. Okay, that's what we mean by inspection. When we talk about ZnCl, I know that Cl is a -1. So if it's Cl- and there's one of those Zns with it, that has to be a Zn+. If I look at my CuO, again, my oxygen is -2. There's one of them, so my Cu must also be a +2. And if I'm looking at CrO4-, I know that overall this is a -1 charge. Okay, I have oxygen, which is -2. There are 4 of them. That gives me a total of -8. So my chromium, then, since there's 1 of them, has to be a +7, because that's the only way that map works. Okay, so that's how we use inspection to determine what those charges are. Questions about that? Awesome. Now, organic materials. Everything that we've talked about so far has been inorganic. What that means is it does not contain carbon. Right? That's what the term organic actually means in chemistry, as opposed to other things. If it does contain carbon, it's called organic. If it doesn't contain carbon, it's inorganic. So when I go to the grocery store and somebody says to me, oh, look, these are those are not organic strawberries, I'm going, okay, they contain carbon, so yes, they are. It's kind of annoying, but that's just the way I do things. So when we talk about organic stuff, we're always talking about carbon, usually with hydrogen on. Hydrocarbons are only carbon and hydrogen. Alkanes are linear chains of hydrocarbons. When one or more hydrogens are replaced by an alkane, they're replaced by functional groups. So an OH group would make an alcohol. Okay, so that's the replacement of that H with an OH group. Okay. Now, is it important that you know that stuff? Well, maybe. If you're going to take organic chemistry, it will be important to you. Are we going to ask you to name some organic things? Yes, and we'll talk about how we do that. But I'm not going to get into how we do the common names, which we'll talk about later too. So, now, for my ionic compounds, I know that Ca becomes Ca2+ and Cl becomes Cl-. Okay, awesome. Do negative and positive charges typically stay away from each other? No, they don't. So if I have a Ca2+ hanging out and a Cl- hanging out, they're typically going to act together, right? So if I'm in the solid state, they're going to come together to make that a neutral. All right. When they do that, that has to be neutral, right? So it's not going to be a CaCl. It's not going to be a Ca2Cl. It's going to be a CaCl2 because I need to have 2 minuses to equal that 2+. Okay. So that's how that's going to work, right? We need to make sure that we have the same thing. So we do something called cross multiplication, right? And you'll see me do this. So I have a Ca2+, I have a Cl-. So this -1 becomes the Ca, there's a 1 there because there's a -1, and the Ca becomes Cl becomes a 2. And of course, then I just write this as CaCl2. So I've taken the charge that's on the negative and put it explicitly with the Ca, the positive species, and the charge that's on the cation and put it explicitly as a subscript for my anion. Okay, so that's how that works. Questions about that? Okay. Well, isn't that fun? So now we know how we put those together, and we can determine the correct formulas for these things, and that's awesome. And I know because they have fixed charges that there's only one way they're going to mix together, so that's cool. Now I have to name things. Why do I have to name things? Because you may see an actual name and be asked what the formula for that is. You may be given a formula and asked what the name of that is. One of the other things that you'll notice, especially in D2L, it's difficult for us to do the subscripts and things for the formulas. So you would probably see that as a name as opposed to a formula. So you may have to interpret that to be able to deal with balancing an equation or doing some calculations or whatever else. Okay. So when we name our ionic compounds, we name the cation, a positively charged ion, followed by the name of the anion, so that negatively charged. The name of the anion changes to IDE. So if I'm talking about chlorine, it becomes a chloride. If I'm talking about oxygen, it becomes an oxide. We indicate the charge of the cation in parentheses and Roman numerals if required. So for those transition metals and those, these guys down here, we would need to do that because we don't necessarily know what that is. So Fe3 is iron 3, Fe2 is iron 2. Common names can be used, but I don't recommend it. Okay. Are there common names that are used? Yeah, actually, and you know a few of them. Water. Water's one of them. So water is a common name. The systematic name for water is dihydrogen monoxide. And you may have seen that around. One of my favorite things as a chemistry student, we used to get these people who would put up flyers once a year that said, ban dihydrogen monoxide. And it would talk about all the different things that water can do to you if you're not careful. And people would get all incensed saying that we need to ban dihydrogen monoxide, and just going, really? And of course, it's mean for us to do that. It very, very much is. But of course, they did this in the tutoring room for chemistry, so it was supposed to be a joke. But again, so common names can be used. Are there common names on your handouts? There should be. Where did I put them? Yes, so on page 8, there's a list of common names. And what you'll see is that there's a common name there. You'll also see the systematic name for it and the formula for it. So in case you need some of these things. Baking soda is one of the things that we typically refer to that way. So that's something you can probably see. Table salt is listed there because table salt is sodium chloride. So that is something that we typically refer to in that way. So if you need to know what that formula is, chances are it's in that table. Okay. So can you name some? If I ask you what's the name of H2O, yes, you can tell me that that's water. Absolutely. Yeah. One of the other things, ammonia is NH3, and that is a common name that we typically work with. Okay. So practice. We're going to name the following, and I'm going to go through the first one in each of these and then ask you to do the rest of them, and I'll come back and work through the answers. So I have an RB2O. So RB is over here. His name is rubidium. So rubidium, because he's written first, so I'm going to write his name like that. And then I have oxygen. He's an O. Yeah, that's oxygen. He becomes an oxide. And again, since it's an ionic compound, that's all I have to do. It's rubidium oxide. So there's no ambiguity in what the charge is for rubidium there, so I don't need to indicate anything else. Now, when we talk about tellurium 4 chloride, right, tellurium, it's one of those T's. That's that one. Tellurium. Okay. He is that one. So he's Te, and he's listed as a 4. So he's Te 4 plus, and then Cl, which is a minus. So I have TeCl4 is the formula for that. Okay. Now, I want to have you guys work through the next few, and I'll give you a few minutes to do that. And then we'll walk through exactly what those answers are. And of course, if you have any questions, yell. Ready for me to trudge forward? Okay. So looking at CaBr2, I know that Ca is calcium. And Br is bromine, so that's a bromide. Mg is magnesium. And S is sulfur, so that's a sulfide. Na3PO4. Na is sodium. And PO4 3 minus, because I know it's a 3 minus, is one of those common polyatomic ions. That's a phosphate. My ZNO, Zn is zinc. And that's an oxygen, so that becomes an oxide. Now, the periodic table that you're given on the exam handouts on page 1 does have names and formulas to help you go between them. So there is that. It's not the biggest in the universe, and I don't take off points for spelling things wrong. So there you go. Manganese 2-phosphate. Manganese is Mn. That's a 2 plus because it's got this 2 right there. And I know that phosphate is that PO4 3 minus. So what I need to do, my Mn, I need to have 3 of them. And then I'm going to have my PO4, and I need 2 of them. So I've cross multiplied this. Plus 2 becomes this subscript down here. The 3 minus the 3 becomes the subscript down here. Okay. Sorry. My zinc 1 nitrate. Zinc 1 is a Zn plus. Nitrate is one of those common polyatomic ions. That's an NO3 minus. So that's ZnNO3. Aluminum oxide. So aluminum is one of those ones that's over here. He's right here. He becomes a 3 plus because of where he is. Okay. So he's an Al3 plus. Oxygen is a -2. So that gives me an Al2O3. Okay. And calcium bromide, shockingly enough, we already talked about. So that's ACaBr2. Is there a reason that I did that? Yes, actually there is. Because that's something that you'll find, is that on a particular test, I may ask you about something over here and give you the formula for it, and ask you about something over here and give you the name. So you may have information on the test that you can use. All right. Make sure that you look everywhere that you have available for information that you may need. I know. Sorry. All right. So hopefully that's good. Questions about that? All right. So we named our ionic compounds. So we've dealt with our metal to non-metal bonds. But we talked about molecules first, and those were our non-metal to non-metal. Okay, well, systematic names are those you need to know. So those are the ones I'm going to expect you to be able to deal with. The common names can be referenced. All right, and again, there's a list of them that are available. Water is one of them. That's fairly common. Binary compounds are named by naming the atom that comes first in a formula, and then name the second item, changing the end to "ide." Oh, this sounds so familiar. This is what we did before. So NO would be nitrogen oxide. Okay. But we know that NO can also be N2O or NO2. So how am I going to tell those apart? Well, that's interesting, because there's not a fixed ratio that these two things have to come together in. So we need to make sure that we indicate which one we're talking about. And the way that we indicate that is by using prefixes for each of those names to indicate how many there are. Now, there is an exception. If it's the first thing, and there's only one of them, we can leave off the mono. Okay, so that is always right. You can always indicate it, but it doesn't necessarily need to be there. So I wouldn't necessarily have to list this as mono nitrogen monoxide. I could just list this as nitrogen monoxide. And of course, I've taken off the second O because it sounds weird. So, but either one is perfectly fine. It is never wrong to indicate the mono in the front, but you are not required to do it. Okay. So if we were talking about N2O, that's dinitrogen monoxide. Okay. And a list of prefixes is given in your handouts. So if you look on, where is it? I think it is. I thought I did. I guess I did. Okay, fine. I guess I didn't actually give the list of the prefixes. I could have sworn that I had. The most common ones that we use are the di, tri, penta. Okay, so di being 2, tri being 3, penta being 5. Okay, but those are the ones that you would need to deal with. And they're given in the table. Table out too. There is one in D2L that has all of those prefixes in it. So there you go. Now, nonmetals and non-metal bonds can be configured in a number of ways. Dihydrogen monoxide is H2O or water. Dinitrogen tetraoxide is N2O4. Prefix that you need to know are on the next slide. See, so it is here. Okay, so these are the prefixes that you're supposed to know. So mono is the 1, di is 2, tri, tetra, penta, hexa, hepta, octa, nona, and deca. Again, typically the ones that we use, the di, the tri, the tetra, and the penta are the most common. There is one specific one that I can think of that's a hepta, and it's a B7, so that's a hepta. But it's not that common that we deal with those. So if I were only going to choose a few that I would memorize, it would probably be those first few. Okay? So those are the ones that we'll need for naming our molecular compounds. Now, compounds containing hydrogen are often non-conforming to our nomenclature rules. So B2H6 is named diborane. CH4 is listed as methane. SiH4 is silane. And H3 is ammonia. These are common names that go with these, okay? So we can use those common names. Note that even the order of writing the elements in formulas for hydrogen compounds is irregular. So normally we would put the H first because it's the positive charge, but in this case, we don't do that. So it's a CH4, all right? So those are things that we get, all right? Now, what does this mean? Well, I'm a flowchart girl, so you get a flowchart. My question always becomes, I need to name something. What type of compound is it? Because what I do depends on what type of compound it is. If it's a non-metal to non-metal bond, those rules are different. And those are our covalent compounds. These things here in the center, those are the molecular compounds. And the covalent has to do with the type of bonding that they have, which we'll talk about later. Okay, so these are non-ionic. They're not composed of cations and anions. So we deal with those rules related to the covalent non-ionic stuff, which means that we need to list how many of each there are. Okay, awesome. If it's an ionic compound, so it has cations and anions, then I'm going to be dealing with the same beginning part. So cation, then name of cation, name of anion, and then I change the last part to an IDE. And we make sure that we've got those in that fixed ratio. The only time that that's different is when I need to indicate what the charge is on the cation. Okay, and that's where I'll indicate that in Roman numerals in parentheses. Okay, so those are our rules for that. You are not going to need to worry about the acids. We're not going to name any of the acids. We're not concerned about that. There are some acids that you will need to know. There is a list of the acids that you are expected to be able to work with on page 7, and those are our strong acids. Okay, so those are the things that we're going to need to be able to do. Okay, so questions, comments, problems on any of our nomenclature? So we will consider ionic compounds, either main group, metal to non-metal or polyatomic, and transition metal to non-metal or polyatomic, and then molecular compounds. Okay, so those are the two cases that you'll need to do. Questions, comments, problems? All right, got a little more practice for you. So, naming a few things, writing a few formulas, and again, I will go through the first of these. So, I have my carbon and sulfur, both of which are nonmetals. So, this is going to be carbon sulfide, but it's a mono sulfide, okay, because it's non-metal to non-metal, so it's a monosulfide. Okay. And when we talk about our aluminum oxide, all right, I'm looking at the formula for that. I know aluminum is a 3+ because he's in this group over here. He needs to lose 3 electrons. 1, 2, 3 to be like the nearest gas, so he's a 3+. Oxygen is a 2-. And so that's an Al2O3. Okay. You get to do the next few, and I'll give you a couple. I swear we're almost done. So, ready for some practice? All right, I have phosphorus. And then there are 5, so that's going to be a pentachloride. And carbon, 2 dioxide. I have 2 nitrogens, so that's a dinitrogen oxide, because there's, and it should be a monoxide because we can only leave the first one off, sorry. CCl4, first one is carbon. I have 4, so that's a tetrachloride. And SeBr2 Se. I believe is selenium. Yep, selenium. It's a bromine. Okay. And it's a dimer because I have 2 of them. Awesome. Now, calcium phosphate. So, calcium is Ca. He is in that second group, so he's a 2+. Phosphate is that PO4 3-. So that's going to be a Ca3 PO4 2. Magnesium oxalate. And what the heck is an oxalate? Well, let's go look. Polyatomic ions. And we'll look for oxalate. Oxalate is C2O4 2-. C2O4 2-. And magnesium is 2+. Sorry, I'll put that in place. So since I have a 2+ and a 2-, it's going to give me an MgC2O4. Okay. And silver dichromate. So dichromate, that is a Cr2O7 2-. Silver doesn't list which charge it has, so I'm going to assume it's a 1 because it can be. So if that's the case, that's going to mean Ag2Cr2 7. Okay. Questions, comments, problems on that? All right, we have 8 more slides. I'm not going to torture you with those today. I'll pick those up on Monday. If anybody has any questions, comments, problems, let me know. I'll be hanging out for the next couple of minutes just in case anybody has anything they want to ask about. Hope you guys have a great weekend, and I'll see you Monday.
Professor,
Yes.
for the lecture quizzes, I've been noticing kind of a trend of there being examples where, like, either like it's like draw something or write out a problem or something else, but whenever I go to do those, either A, I don't know how to draw something in text, or B, when I write out the problem, it's been giving me like 0.7% of the entire grade.
Well, okay. So, and that brings up an excellent point. D2L is not great on grading on its own. It is my job to go back and regrade those things because D2L doesn't know what to do. And I will tell you this point blank. The point of those quizzes is not to give you any points. Okay, you get points for doing them. Yes, absolutely you do. But if you take them, you get all the points. I need to know, did you understand? And if the class didn't understand, then I need to go back and cover that again. So that's what that's for. It's designed so that I can see if you guys are understanding. For today, for what got done today, I should have indicated when I did that I just wanted to know how many electrons, how many protons, and how many neutrons needed to be there, as opposed to making you draw it.
Okay. Because I just put, I don't know how to do this over text because I didn't know what else to put.
And that is okay. That is perfectly fine.
All right. Thank you so much, Professor.
Sure, no problem.
I have a quick question.
Yes.
About that drawing. Like, I'm a little confused on it. Are you able to help me with it? Or
Yeah,
is
sure.
it not like, okay. So,
About
like, you know how you have, okay.
the one we did at the beginning, right?
Yep.
What's your question? Like,
Yeah, so, like, for the first one that we did, I don't know if I was, hold on, let me,
somewhere.
okay. You see how we did, like, the, fluorine, I believe? That's what we did in the
Yep,
beginning?
correct.
Yeah, so that one, it was 13.9 fluorine minus, I
Yes.
believe. So how did we get 1 to 10 electrons?
Okay.
Was
So
that because of that negative in
correct.
front that made it
That's why.
10? Okay. And then neutrons is just like 13 minus 9 that
Correct.
makes neutrons. And
Correct.
electrons are 9. It
If it was neutral, it would be 9. Correct. Since it's a minus, we have 1 more.
so
Protons are 9 because that's the number down at the bottom.
also protons are 9, electrons are 10,
Correct.
and the neutrons are 4.
Correct.
Okay. Okay. And then how do we upload our picture again? We
So
just take a picture of it?
if you you can take a picture of it. Again, for this time, I wouldn't worry about it too much because everybody's going to get full credit. No big deal. But what you will see, and there should have been, in the assignments, there are drop boxes for scratch work, and there should be
Okay.
one for quiz scratch that goes here, but I have failed to put one up yet, so I will make sure I do that right now.
Okay.
So yeah, you can take a picture of it and upload it there, and I can take a look at it.
Okay. So I don't need to worry about this one, right? Or
No,
you want me
you,
to? Okay.
you do not need to worry
So
about this one.
yeah, and one more question. Are these quizzes based on finishing them or by correct answers and stuff?
No, so it's a did you do it, did you not do it is how you'll get your points.
Okay, so if I did the quiz, if I attempted to do the quiz, then
Yes.
yeah, you'd
Yes.
okay. That makes
That
more
is
sense
correct.
because I was confused. Like on my first quiz, I only got 1.7. I was like, dang, I'm already off a bad start. So-
Again, that is for me to be able to look at, did people understand that? And if they didn't, what do I still need to talk more about? So
Right, right.
yeah, that's what
Okay.
that's for. And I will be going back and quote unquote regrading those to give feedback and to make
Okay.
sure that those points are assigned appropriately.
All right. Sounds good. Um, I think that would be all for me.
Okay, awesome. Thank you
Thanks.
very